Namaste and welcome to this lecture on mathematical foundations of machine learning. In the last lecture we were looking at the Chebyshev inequality and we looked at central limit theorem, just had some example where we understood a few points about the central limit theorem. I just deal that in detail in this class and then we will go ahead looking at sample geometry, and then we will look at the idea of covariance matrices or covariance matrix and so on. So, when we did in the last class, what we did in the last class was we looked at Chebyshev inequality, where we said that look, given a random variable, a real valued random variable, any real valued random variable, we said that if this random variable is going to have a finite mean and variance, then the probability of the deviation, finding the random variable beyond certain standard deviations is less than or equal to 1 by n squared. Suppose you want to look at n standard deviations, the probability of finding out a random variable beyond n standard deviations, then we said that this probability is less than or equal to 1 by n squared, which is pretty which you can easily understand when you look at, let us say, the Gaussian curve or something, where we say that beyond the deviation the probability of finding the random variable reduces beyond n standard deviations where n is fairly large, and that is exactly what our Chebyshev inequality gave us. And after that we did something interesting. What did we say? We said that look, this is fine, Chebyshev inequality and the what would you call Markov inequality, these two guys were independent of the distribution, underlying distribution that was associated with the random variable x, right. We did not know, we did not really care whether the random variable was discrete or continuous, we did not care whether the random variable was especially in the case of Markov, we said it could be a non-negative random variable, it could be any real valued random variable. We did not really care basically about the distribution that the random variable x had, and we were able to get a very good bound on the tail probabilities, right. And then what we did, look, I have samples, I mean I have a population, I have a huge population. Now what I wanted to do is I really wanted to figure out like if I sample the population, because I can't really get the entire information about the population as such. So what I do is I typically take samples, and then what we did is we took the sample mean, we just took the mean of the samples that you take out of the population, and the samples must be, let us say, of the same size. Assume that we had the same size samples and we took a sample of size n, and you take multiple such samples, right. So what you do is for this sample, for every sample of size n, we found out the sample mean. The population on its own had its average, every sample that you pick out will have its average. Now what we did is we did something interesting. We took the average of all the averages. We said that look, I will take the average of the sample SA S1 which contained n elements, I will take the average of the sample S2 which contained n elements, and so on. I will collect the sample of, let us say, I will keep collecting the sample means, let us say, of the kth sample Sk which also had n elements. Now what I do is I take the average of all these k samples, and we found out something very interesting. What was that? The average of the sample mean it is equal to your population mean. That is what we found out. And what is interesting is not just that, as you increase the sample size you have more what would you call a more accurate result that you get. So as the sample size increases, we said that look, the sample mean, the mean of the sample mean, or the mean of the sampling distribution, we call it the sampling distribution, the mean of the sampling distribution converges to the population mean, and the mean also has the mean is basically the sample mean is basically a random variable. We saw that, right, when we took those 5 numbers 1, 2, 3, 4, 5 in the previous lecture. We saw something interesting happening. What we said is like, look, I will take sample size of size 2 all the samples were of the same size too, which you can very clearly see here. And then what we did, we added all the averages and then took the average of all those fellows, and we found out this mean was basically equal to what the population mean was, that was 3, and this also you get it as 3. And then what we did, we further increased the sample size to 3, and even there we figured out that, look, this is interesting, even there the mean of the sample mean converges to the population mean as the sample size increases. You could actually check it for n is equal to 4, n is equal to 5, and then we made some statement about the central limit theorem. What we will do is we will just take another example to see this. In fact, we will visualize all these things and then see like what happens, right. So what I will do is I will just take a small example here and then start looking at I mean we will make the final statement for the central limit theorem, after which we will start looking at our sample geometry. Okay, so here is today's class. So we begin this today's class with basically a simple example of tossing a pair of fair die. So let us consider tossing a pair. Okay, let us do a tossing of a die first, let us do that. So tossing a single die, tossing a single fair 6-faced die. One more thing that you can look at is even you can look at the tossing of a coin, which is very simple experiment. You toss the coin once, what is the distribution? A fair coin, what is the distribution? Of course, it does not depend, I mean you do not really have to worry about the distribution, it be fair, it need not be fair. So what we will do is we will just take a look at what is the, I mean we are going to have a fair 6-faced die. What we are going to do is we are going to toss this single fair 6-faced die. The first one is I will do a single toss. So let me do a single toss of a fair die. So if I say the moment fair die, then we understand something, that means the probability of getting each of those 6 numbers is the same as the probability, one of those numbers is the same as the probability of getting any other number in the set 1 to 6. So we are going to have the sample space to be equal to 1, 2, 3, 4, 5 and 6, and then what we are going to say is like single toss of a fair die. Therefore I have probability of 1 is equal to probability of 2 is equal to etc is equal to probability of 6 is equal to 1 by 6. This is what I have. Now if I look at the expected value of x, which is basically the average of this, now we know what is the average. The average of this is nothing but what is the average? It is 1 by 6 into 1 plus 1 by 6 into 2 plus 1 by 6 into 3 and so on. We are going to have the average to be equal to 3.5, right. That is going to be the average which we get. That means this is the mean we have, mean is 3.5. Now what I am going to do is I am just going to draw the probability distribution here. I am just going to have the probability distribution of these numbers. So I have all of them to be at the same height, which is basically 1 by 6, right. This is like 1, 2, 3, 4, 5 and 6. I am going to have my probability mass axis here, Px of I, and all of them are 1/6, right. This is what we have. Now what I am going to do is I am going to take a sample size of, say a sample of size 2. What I am going to do is I am going to toss the coin twice. I am going to roll the dice. Okay, I am going to roll the dice twice. So what am I going to do here? I am sorry, I am going to roll the dice twice. I am going to roll the dice twice. Now what am I going to do? if I roll the dice twice and then what I do is I am going to record, I am going to and look at the sum of the two rolls, look at the sum of numbers on the top face. Okay. So, on the top face of the die. Right now, okay, this is roll the die twice. Now, what am I going to do? This is the sample that I have. This is basically the population that I have, where it is going to be 1/6 and so on. Now, what I am going to do is I am going to take sample of size n is equal to 2. So, let me take sample of size n is equal to 2. So, sample of size n is equal to 2, right. Now, therefore, and then what I am going to do is I am going to look at the sum of the two tosses. So, what I am going to do, the first toss I am going to call that as x1, I am going to represent the outcome of the first toss by the random variable, let us say x1, and the second toss I am going to represent by the random variable x2. Therefore, what we will have, we are going to have sum for this, which I am going to write this as sigma xi, which is nothing but let us say x1 plus x2 in this case. Now, if you look at this, what we are going to have is, so I am going to have the first toss can be any of these numbers. So, let us say the first toss can be any of these numbers, the second toss can be any of these numbers. So, what am I going to have? I am going to have these numbers 1, 2, 3, 4, 5 and 6. Similarly, I have numbers 1, 2, 3, 4, 5 and 6, and now what I want is I want to basically look at the sum which is x1 plus x2. So, I am going to have 2, 3, 4, 5, 6, 7, then I am going to have 3, 4, 5, 6, 7 and 8 and so on. So, I have 4, 5, 6, 7, 8 and 9, then 5, 6, 7, 8, 9 and 10, 6, 7, 8, 9, 10 and 11, and I am going to have 7, 8, 9, 10, 11 and 12, right. Now, what I am going to do is I am going to look at the, so this is basically whatever that we have is basically if you look at this, I am going to have the numbers from 2 to 12, and here what we see 2 appears only once, 3 appears twice, 4 appears 3 times, 5 appears 4 times and so on, and 10 appears thrice, 11 appears twice and 12 appears once, right. So, what am I going to do? I am going to have my probabilities of these numbers. What are the probabilities of these numbers? There are 36 outcomes totally here, and this 36 outcomes implies you have probability of 2 is equal to 1 by 6, probability of 3 is equal to 2 by 36, probability of 2, oh sorry, I said 1 by 6, this is going to be 1 by 36, this is 2 by 36, 3 by 36, 4 by 36, 5 by 36, 6 by 36, 5 by 36, 4 by 36, 3 by 36, 2 by 36 and 1 by 36. Now, what we will do is let us plot the probabilities. So, what am I going to have? I have numbers like this. So, I have numbers beginning from 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12, and the probability values are going to be, as I said, this is going to be 1 by 36, this is going to be 1 by 36, this is going to be 2 by 36 and that is going to be 2 by 36. Then you have 3 by 36, which is basically this is going to be 3 by 36 and that is going to be 3 by 36. Then you have 4 by 36 for 5 and you have 4 by 36 for 9, then you have 5 by 36 for 6, you have 5 by 36 for 8 and then you have 6 by 36 for 7. So, these are all the probability values. Let me write this. So, this is 1 by 6, I am going to write this as p x of x, 1 by 36, 2 by 36, 3 by 36, 4 by 36, 5 by 36, 6 by 36, right. This is what we have. Now what we will do is we have to figure out where is this basically centered, where is the center of this distribution, right. We need to figure out where is the center of this random variables that you have. You could still do the same thing. You will get 2 into 1 by 36 plus 3 into 2 by 36 plus 4 into 3 by 36 and so on. You would see something interesting here. You will see that this distribution is also centered at mu is equal to 35, right. This you would see this is also centered, this is so. What are we going to do for the average? We are going to take the sum. So, average here is basically sigma xi by 2, that is x 1 plus x 2 by 2, because the average you are taking only 2 samples together. You have tossed the die twice, which means you take the first, you take the second and then add the sum by 2. So, that is the average of the 2 tosses. So, you are going to get this. If you do this, you would still end up getting the center to be at 3.5. Now what you do, you slowly increase the number of tosses, you keep increasing the number of tosses. As you keep increasing the number of tosses, what we would see is the sampling distribution. This is basically what we call as the sampling distribution for sample size 2, sampling distribution for n is equal to 2, right. You could actually do sampling distribution for n is equal to 3, n is equal to 4 and so on. That means you toss the coin thrice and get the average, take the sum of the 3 tosses, find the average of these 3 tosses. You can toss the coin 4 times, then the sample size becomes 4. Now what you do is take the sum of the 4 tosses, take the average, all of them you would see something interesting happening. You would see that the sample mean would still be would still be centered at the value which is 3.5, which we got as the population average there. And if you start looking at the shape of the distribution, the shape of this distribution would slowly become a normal distribution, right. It would slowly start becoming normal distribution. I will just show you one more example from which you can understand. Suppose I take a toss of a coin, toss of a fair coin. So, the initial distribution, toss it only once. So, you are going to have probability of head is equal to half and probability of tail is equal to half, say. Then what I do, I toss a coin twice, toss a coin twice. Now what are we going to do? We are going to look at, basically you can look at this. So, what am I going to do now? As I toss the coin twice, now I could see that the number of, you count the number of heads. So, what are we going to get? I am going to have no heads, I am going to have 1 head, then I am going to have 2 heads, right. So, this is going to be 1 by 4, this is basically probability half, p of xi is basically half here. In this case p of xi, I will put this as 1/4, 1 by 2 and 1/4, right. Now what we have done is you can basically see this is basically the distribution of the entire set of numbers. What we want to do is we want to look at the distribution of this mean, we want to look at the distribution of the mean. So, what are we going to get? If you take the first one, the mean can vary from, let us take this. So, let us look at this case and then go back there. So, the mean in each of these cases, when you take the first 1 1, so the mean is going to be I will take it as xi bar. So, it is going to take a value 1, then I am going to have 3 plus 3 6 by 2, the average is 3, then I have 4 plus, so I have to take basically 2 numbers each. So, what we will do is let us better do that and then get back here. Let us get to that and then do this. So, what are the possible pairs that we get from the roll of the 2 die? Let us take that. So, it is going to be whenever so you have 1 1. Let me do it here, sorry for this goof up. Now what I will do is I will take the average of these two die and then write it in a different color. So the average here is going to be 1, right, the average here is going to be 1. Right, the average is basically marked in this color, sample mean is basically marked in this color in this figure. So this is going to be, then you have 1 plus 2 by 2, the average is going to be 1.5 here. Then what is it that we are going to say, it is 1 plus 3 by 4, the average is 2 here, then 1 plus 4 by 5 which is going to be 2.5, 1 plus 5 which is 3, then 1 plus 6 is 3.5. Similarly I am going to do the same thing, I have 2 plus 1 which is 1.5, then I have 2 plus 2 4, the average is 2, right. So I am going to get these, the purple color values that I am doing here, these are all going to be my averages here. So then I have 2.5 here, this is the average, this is going to be 3 and this is going to be 3.5 and that is going to be 4. Similarly I have the average is 2 here, the average is 2.5 and so on. Now if I plot this set of averages that I have, if I get the distribution for these averages, I would see that it would still be centered at 3.5. That is exactly what we meant, right. We have 1 to be we have 1 to be appearing only once, and then 1.5 to appear twice, then 2 to appear thrice, then 2.5 4 times, 3 is 5 times and 3.5 is 6 times. So we will have a distribution like this. 1 will be, let us say this is going to be 1, 1.5 is 2 times, then 2 is going to be 3 times, 2.5 is 4 times, 3 is 5 times, 3.5 is 6 times, 4 is 5 times, then we have 4.5 is going to be 4 times, then 5 is going to be 3 times, then we have 5.5 to be 2 times and then we have 6 to be 1 time. So this is basically the average. So average of the 2 dice, 2 rolls, okay, of the die. So this is going to be 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5 and then 6. This is what we have. Now you keep increasing the number of tosses, keep increasing the number of rolls, that means you are going to say x1 plus x2 plus x3. I am going to look at 3 rolls and then I am going to see what is going to be the sum. So if you see, if you look at the distribution of this x bar, this x bar will have a distribution which is slowly converging to a normal distribution, right. So from the figure what we see is the distribution of the sample mean tends to become normal distribution as you increase the sample size, and that is exactly what the central limit theorem says. So let us look at that. So what we are going to say is, if, so this is the statement of the central limit theorem. This is the statement for central limit theorem. What we say is, if random samples of, let us say, n observations are drawn from a non or from a population with any distribution, let us say from a population assume that the population distribution is, say, non-normal, population which is non-normal with finite mean, mu and standard deviation sigma then for a fairly large n right, for a fairly large n, we say that the sampling distribution of the sample mean x bar is approximately normally distributed with mean mu and standard deviation sigma by root n. And what we are going to say is, as n tends to be extremely large, as n becomes larger and larger, the approximation becomes more accurate. Right. Now, the other way of looking at it is, it is like saying, look, if you take n large, I mean very large sample size, then it says the sampling distribution of the sample mean has standard deviation which is sigma by root n. Therefore, if n is fairly large, the standard deviation becomes smaller for the sampling distribution of the sample mean. That means your variation of the sample the sample mean of the sampling distribution, right, your variation tends to, from the actual population mean, tends to become small. The error between the sample mean, the sampling distribution, the sample mean and the actual population mean becomes smaller and smaller as n tends to infinity, which is or as n becomes large, which is very evident from the fact that if the standard deviation of the sampling distribution of the sample mean is basically sigma by root n. That means, as n increases, the standard deviation sigma by root n tends to decrease. That means, we are going to get the normal distribution to be narrow and narrow. And what is it to say narrower standard distribution? That means the variance is going to be less. That means the sample mean is not deviating much from the population mean. We have already seen that it is always centered at the population mean, but then with some variance. But as n increases more and more, the variance becomes smaller and smaller, therefore the approximation becomes more accurate. That is the crux of central limit theorem, right. So, what does it say? It just says like, look, regardless of the shape of the distribution, the shape of the distribution, the sampling distribution of x bar, that means the sample mean, will always be normal distribution as the sample size increases. It always has a mean identical to the mean of the population, the sample population, and a standard deviation equal to the population standard deviation divided by root n. So, this what we actually say is, let us make this statement, and then before we wind up this idea of central limit theorem and then get on to sample geometry. So, what it means is, we say that the spread of the distribution, the spread of the distribution of the sample mean, distribution of the sample mean is considerably less than the spread of the sampled population. Okay. So, this is the crux of our central limit theorem. Now, one thing that we have noted is when we discuss central limit theorem, we had always been talking about sample mean, sampling distribution and stuff. So, the next question that we are going to ask is, we understood what is sample, but next question that we are going to ask is like, is there a geometry that is associated with the sample? So, the question we ask is there a geometry associated with sample? So, can we geometrically interpret a sample, and that is a question that we are going to ask in the next lecture. So, in this lecture what we have done is we have actually looked at central limit theorem, we looked at another example compared to what we did before. We were talking about the average of rolls of die and then keep increasing the number of rolls. We said that the average kind of converges to the average of the sample means. We said that it becomes equal to the population mean as the value of n increases, or as the value of as the sample size increases, that is what we said. So, what we do is we are going to conclude this session with a question, where the question is there a geometry associated with the sample? Can we look at the sample geometrically? Because one thing is like it is always going to help us if we have a geometrical association, to the sample, because it is going to be some kind of a vector. If that is the case, then it is good, because we have already done the idea of vector spaces, and then a lot of things are revolving around the vectors idea. We could employ all those things in analyzing our sample. So, we will see the answer to this question in the next lecture. Namaste.